send
this
them.
still 16.2?
This is still 16.2.
Oh, jeez.
So let's just recap here for a moment. We did, oh boy. Hold on. Hey, alright. So with the first part 1, we did on page, where's my book? Hold on, 16.2. It's page 1096, right? So the first part of the assignment we did 1, 3, 5, and 9. The next part, same page, we just did 7, 8, 14, 11, okay, so 7, 8, 14, 15, and 16. We got no questions on those, right? And that was, so this was line integrals, and that was, did we not do? Oh, we did 14 together. I did it as an example.
Oh, okay.
That's what it was. To show you that. So now we have one thing left. And there's 2 more problems we're going to do. So there's part 3 is going to be on line integrals. Of vector fields. Okay. So first of all, you all know for work is equal to force times distance. So well, I'm assuming you know that. So we went along in your science class. Learn that. And then in Calc 1, we do work with a variable force, so an equation with force, and work is done given that force equation. This is force here. So it's really the same equation. This is the distance here, dx. And I don't know if we ended up doing any work problems, and you guys did Calc last year, and I came up with examples, but you know, the idea is to divide this, each of those pieces is dx, so the integral adds up the work done for every single piece is what's going on. Okay? Now, we're going to do the work done by a force field on a particle moving along a path. And by a path we mean a given curve or equation. And you can look at a lovely picture on page 1095. So you see that little in the middle on the left hand side, a vector, this force field. All the blue lines are this force field. The length of the line indicates the magnitude of the force, and then the arrow is the direction of the force. And the red line is this particle traveling along that curved path in this case. And you can tell with the red arrow which way the particle is going. So right off the bat, what's the force field going to do to that particle? Slow it down as it's going, they're going against each other. Alright, so the work done, so the little formula, the work done by a force field on a particle moving along a path or curve is given by the integral along this curve. C is the curve. In other words, think about it that way. Capital F, this is your continuous vector field, force field, dr. So this is our goal, and you're going to do that by taking the integral from a to b of the composite of f of r of t. This is your vector. Dot product with r prime of t dt. And it's been a while, yeah, since we did dot products, but we're going to refresh our memory with that. Okay, so this curve is given by vector rt. So this will make more sense when we do an example. We're going to do example 7. That page. It says, find the work done by the force capital F of xy equals x squared I minus xyj. And so there's your force field vector for that. So in moving, work done in moving a particle along the quarter circle r of t cosine of t I plus sine of t j. Oh, and then you're told t is going to go from 0 to pi over 2. Put that into there, it's a composite, and I'm going to show you because this will be x and that will be y. And you dot product with the derivative of this. That's what's going to happen. So, according to our little r of t here, we can see that x would equal cosine of t, and y would equal sine of t. So f of r of t, putting those into that given equation. So first x squared would be cosine squared of t I minus, and then for the xy, it's cosine of t sine of t j. So we just took these and plugged them in there. Okay. And now we're going to take the integral. So from 0 to pi over 2 f of r of t dot with r prime of t dt. shove in here the derivative of this, r prime. So r prime of t, the cosine would be negative sine of t j plus cosine of t, I. So negative sine of t I plus cosine of t j. So if you remember, the dot product just simply means you multiply together the corresponding components together and then add them. So this dot r prime is going to be cosine of t squared times negative sine of t, or negative cosine squared t sine of t, plus this negative cosine t sine t times cosine of t. So that would end up being negative cosine squared of t sine of t dt. And it turns out you got two of those exactly the same. You can pull that negative 2 out front. And we can use substitution on that. We'll let u equal cosine of t, du dt, negative sine of t, so du negative sine of t equals dt. Or you could have just left that over there, however you want to do it. So when we plug this in for here, the signs will cancel, the negative will cancel. Just get the integral from 0 to pi of u squared du. Oh, I forgot the 2, didn't I? Alright. Add 1, divide, 3, 2/3, u cubed. So it's 2/3 cosine of t cubed from pi over 2 to 0. Cosine of pi over 2 is 0. So 0 minus cosine of 0 is 1. Cubed is still 1. Minus, so we get 2/3. So you get negative 2/3. That's the work. And it is negative because it's acting against the object. It says here, because the unit tangent vector t is, oh no, that's not what I want to read. The work done is above the picture. The work done is negative because the field impedes movement along the curve. You know what I'm saying? They're going, the force, as we knew already, was slowing it down. Okay, so we have these specific kind of problems. Just 2 of them I want you to do. So 1097. 19 and 21.